This is Mr. G Math. Juan, you can't leave. You can't leave. At the beginning of the video. You just ruined the video. Live, right? 72 room 7202. What the hey, Juan? You leave right when I start the video. All right. This lesson's also on limits, but involving infinity. So, the graph of this function here, look at it carefully. At what x value is there a hole? So look in your packet, work with me, and if I go too quickly, these videos are there that you can go as slowly as you need to so you understand what's happening. When does a hole exist in a graph? What would you see happen? Something would have to divide out, correct? And so in this case, what factor divides out? Now, if something divides out, it has to be completely removed from the denominator. So if something simplifies, but it still remains, that's not a hole. It's got to be removed, which it is. So what is the factor of what was removed? And if you take the factor of what's been removed, make it equal to 0 and solve it, at what x value is there a hole? So can you see the connection there? An even vertical asymptote. The concept of even and odd, similar to end behavior, where if something's even with an end behavior, both ends go up or both ends go down. So if it's an even asymptote, that means the exponent in the denominator, where you get the asymptote from, is even, which means both ends either go up or both ends go down. Can you see the picture of that? So that means the left and the right side agree, right? Either to positive infinity or negative infinity. And if it has an odd exponent, it means they don't agree. One side goes to positive infinity and the other side goes to negative infinity. Do you see the pictures below between even and odd? So where is there an even asymptote? Can you see the even exponent? What's the factor connected to it? Make it equal to 0 and solve it. Where is there an even asymptote? At x equals 2. And that has to do with the exponent. Yes? Okay, where is there an odd exponent for a vertical asymptote? Can you see the odd exponent? Yeah. What vertical asymptote comes from here? 4. Now, what does that mean? If it's an odd exponent, one end is going to infinity, and then on the other side it's going to negative infinity. They go in opposite directions. Even, they both go to positive infinity, or they both go to negative infinity. All right, let's keep reading. Infinite limits. You have seen examples where a limit does not exist at a vertical asymptote. Such non-existent limits can be expressed as infinite limits if the vertical asymptote is even, or if you are finding one-sided limits. So we will write that the limit as x approaches c of f at x equals infinity, or the limit of x as x approaches c for f at x equals negative infinity. The examples below make use of your knowledge of even and odd vertical asymptotes. Welcome back, Juan. Thanks for coming back. As well as holes. Okay, so look at number 1. When x equals 2, does that make a hole or an asymptote? When x equals 2, is this a hole or an asymptote? And why is it an asymptote? Because it's non-removable, right? If it could be removable, then it's a hole. Now, if I drew a picture of this graph and found where positive 2 was and did a dashed line, do you know what side would go where? Because it's saying from the right. What direction does it go? So the best way to understand this is to plug in a number larger than 2 and see if the answer is positive or negative. So if you plug in a number bigger than 2, is the answer positive or negative? That means the right side is going to positive infinity, while the left side is going to go to negative infinity. Why? Because what exponent there that you don't see? 1. So from the right, the answer would be positive infinity. If you take the same question from the left, the answer would be negative infinity. Can you see how we did a quick little picture to see that? It's odd, and we just plugged in a number to see whether it was positive or negative. Okay, look at the next one. At x minus 1 squared. When x approaches 1, is it approaching an asymptote or a hole? Good, because it's not removable. So when I think of positive 1, is it coming from the right or left? Is it above or below? Plug in a number bigger than 1 and see if it's positive or negative. Try again. Well, try a number like 1.5. So, like if you plug in a number bigger than 2, it's going to be positive, right? That's because at 2 is an intercept, right? Positive 2. You need to plug in a number between 1 and 2. Don't plug in a number bigger than 2, because that's an intercept at 2. Between 1 and 2, what do you notice? And I want you to notice the answer is negative. Like what's 1.5 take away 2? Negative. What's 1.5 take away 1 and square it? It's positive, and when you divide, the answer is negative. Guess what's on the other side then? And the reason is because the exponent is even. So, from the right side, where does it approach? Negative infinity. From the left side, where does it approach? Same one. Negative infinity. And what's happening for number 5? Is this a asymptote or a hole? How do you know? So you first have to simplify it and see if it's removable, correct? The numerator is a difference of squares. So factor it. What do you notice about x minus 2? It divides out. So that when you plug in 2, the answer then is 4. Because it's removable, right? All right, turn the page when you're ready. Now I want you to notice what's different about this side is that the limit is approaching infinity. Not that the answer could be infinity. The answer could be infinity or negative infinity, but it's approaching it. So we've talked about this last week too. So if the graph of a function approaches a horizontal asymptote to the left and or the right, it is said to have a limit at infinity. If the asymptote y equals L, then that limit is whatever the horizontal asymptote is. So in other words, limits at infinity give us n behaviors for graphs. For large values of x, the highest degree terms in the numerator and denominator dominate the other terms and are the only terms you have to consider. So in other words, all you have to do is look at the power term. Okay? So if I said at the top, it says find the horizontal asymptote. What's the power term on top? 5x to the 4th. What's the power term on the bottom? When you simplify it, what does it simplify to? So, where is the horizontal asymptote? At 5 over 10 or 1/2. Look at the next one. What's the power term on top? What's the power term on the bottom? So what's the horizontal asymptote? Why is it y equals 0? Because the degree on top is smaller. Whenever the degree on top is smaller, the horizontal asymptote is always y equals 0. What's the power term? What's the power term? What's the horizontal asymptote? And you'd write down, there's no horizontal asymptote. Why is there no horizontal asymptote here? Because the degree on top is larger, right? So a horizontal asymptote only exists when the degrees are the same or the top is smaller. All right, let's take that understanding and find limits at infinity. What's the power term and the power term? We just did this. And so what did it simplify to? So what's the limit as you go to infinity? And the answer is the y-coordinate's getting closer to 1/2. So as you go to positive infinity or negative infinity, it's going to get closer and closer to the horizontal asymptote. So what's the y value it's getting closer to? Look at the next one we just did. What's that limit going to equal? And why does it equal 0? Because there's a horizontal asymptote. Jerry.
Isn't it asking to find the limits?
That's what we're finding. So what we're finding is this, Jerry, that the horizontal asymptote and the limit at infinity are the same. So as the function goes to infinity, what you're asking is, what's the end behavior of that function? And if a function has a horizontal asymptote, the function always goes to that at the ends. So what's the y-coordinate it goes to at the ends? It's the same as the horizontal asymptote. So number 11, is there a horizontal asymptote? No. So does the limit exist? Right? So it doesn't exist because it doesn't go to a y-coordinate. 12. What makes this one challenging? It's factored. We have to expand it. But we only care about the power term. So how can I quickly find the power term? 2x times what? X squared. What would that be? 2x cubed. Correct? How do I find the next power term? X times, be so careful here, 3x squared. Can you see why you have to be careful? Because 3 squared is 9. And if you don't include 9, you're not going to get the right answer. Can you see that? You have to square 3x. So altogether, that is 9x cubed. The x cubes divide out. And what is the end behavior? What y-coordinate is it going towards? 2/9. Can you see how easy it is to not have 9 included? Horizontal asymptotes is that limit, right, to infinity. Number 13. It says, rational functions like those have at most one horizontal asymptote. Here are examples that have 2 horizontal asymptotes. Isn't that crazy? Can I tell you why there's 2? Because when you solve a quadratic, the answer could be positive or negative. So what is the power term on top? Is the square root of 4x squared. Well, we know the square root of 4 and x squared would just be 2x. But the answer could be positive 2x or it could be negative 2x. And that's divided by what? X. So what are the 2 horizontal asymptotes? Positive 2 and negative 2. And the question is, as you put in larger positive numbers, is it getting closer to positive 2 or negative 2? So as this goes to infinity, it's going closer to positive 2. Can you see that? If you plugged in 10 or 100 or 1,000, the answer is getting closer to positive 2. What happens if you go the other direction, from negative infinity? Negative 10, negative 20, negative 30, negative 100. What answer is it getting closer to the left? Negative 2. So there's a different looking function that has 2 horizontal asymptotes. So in other words, it has a floor and a ceiling, and it's squished in between the two, the whole picture. All right, over and out. That was it.